Yes, I'm still wearing the same shirt. I don't know. It must be weeks into this whole mess. So, time to do laundry, I suppose. Last video, we were talking about dot products. I went ahead and wrote the formula up here. And the formula says A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them. And just remember, a dot product accepts two vectors and produces a scalar. The interpretation of a dot product is that it can be used to measure the shadow of one vector in the direction of another. That's sort of a rough, intuitive bit. Here's what you can do. You can think of it as dot products pull out the pieces of vectors which are parallel, because perpendicular vectors don't contribute to the dot product. So the dot product is useful for grabbing parallel information between two vectors. Should have said it that way last time. I just didn't. On the other hand, we're going to have a second way to multiply two vectors. And the second way to multiply vectors is not going to know about the parallel information. It's going to know about the perpendicular information. So between dot products and cross products, you can figure everything out. Roughly speaking, that's the idea. Dot products know about parallel stuff. Cross products are going to know about perpendicular stuff. So they are complementary bits of information. Okay, so I was thinking about the last video, and I started with the algebraic stuff. I think what I'm going to do now is start with the conceptual stuff, maybe the picture part, and then work out the more formal stuff next. I think that's a better way to do this. I apologize, first time doing these videos. And what comes off okay in class sometimes doesn't come off okay in these. So apologize. Okay. Now, one of the tricky things with cross products is that they are inherently three-dimensional beasts. Okay, so when you have, you just always have to deal with 3D stuff. All right. So here's going to be the deal. Let's imagine that you have 3 dimensions, and we always use a right-hand coordinate system. We have x. As you look down in the kind of positive octant, you would have x, y, z cyclically in that order. So if you look down at the origin, hovering in the first octant, looking down at the origin, as you went around counterclockwise, you would have x, y, z in that order. Okay, so that's important. Make sure you can picture that. And then if we were to have two vectors, A and B, oh dear, this is going to be a mess. I apologize. A and B. What you could imagine is that A and B, so these are two vectors, they live in 3D. Well, if you think about it, just picture it in your mind or do it with your hands. Two vectors in 3D are actually going to define a plane. So what you could imagine is I have these two vectors. Imagine like a soap bubble kind of spanning the gap between them. Then that would define a surface where the two vectors would lie in that plane. So here's my two vectors A and B. I'm kind of trying to draw them sort of, I don't know, going out there some way. And what we're actually going to do is imagine these vectors, they define a plane, but in particular, I don't want to just focus on the whole plane. What I want to do is focus on a parallelogram that they subtend. I think that's the right word. That they span. That's probably a better way to say it. So if you took these two, you can imagine that they sort of sweep out a parallelogram. So, okay, and make a little like a little, it's kind of like, I should have brought my, one of our pirate tissues, our pirate handkerchiefs. All right, but if you have two vectors, okay, I can imagine if I have two vectors, 1, 2, then they kind of sweep out a parallelogram on the board. Okay, two vectors, they sweep out a parallelogram on the board. Well, now to get it in 3D, just kind of lift it off the board and put it wherever you want. That's the idea. Okay. All right. So here's the deal. The cross product between A and B, this is going to, so it's going to take two vectors, A and B, and it's going to produce another vector. So a dot product takes two vectors and produces a scalar. A cross product takes two vectors and produces a vector. You say, ah, awesome. Why didn't we start with this? I mean, this sounds like the way we should have defined product in the first place for vectors. Well, you know, could be because I'm a jerk, which, you know, is fair enough. But no, the reason is it's going to be more complicated than you probably imagine if you haven't seen this before. So the answer to the cross product between A and B is going to be a vector, and the magnitude of that vector is going to be the area of this parallelogram. Okay, so the area of this parallelogram formed by A and B is the magnitude of the cross product. So I'll go ahead and write this out. A cross B, whatever that means, I'll have to figure that out, has a magnitude which is the area of the parallelogram. Parallelogram. That doesn't look right. That doesn't look right. Well, you know, I could use my old Spanish trick and just kind of put in whatever you want. All right, parallelogram. I don't know. We'll go with A, parallelogram. Sure. I have no idea. Anyway, area of the parallelogram. So, and the formula for that, it turns out, is the magnitude of A times the magnitude of B times the sine of the angle between them. Okay, so you can see that in the plane. So if I just draw a vector, A and B, then, well, a little bit more forethought, I could make it fit. I make this parallelogram. Okay, these are parallel, right? So immediately you see that you could chop this triangle off and basically fill in the gap. So you can take it, chop it off here, and simply migrate it over to the backside here, so that you end up with a rectangle. Okay, because they're parallel, so you can slide them without changing the area. And when you do that, the area of this would be the base times the height. So that would be the magnitude of A, and the height of this would simply be the magnitude of B. I have too many little lines here, it's getting cluttered. All right, what's the height of this? Well, if this was an angle theta, the angle between the two vectors, I should have said that, it's the angle between the two vectors. The height of this is B sine theta. Okay, so the area of the parallelogram is A times B times the sine of theta. All right, Awesome. You say, well, piece of cake. Why didn't we do this one first? It's got a simple formula, and it gives you a vector. I haven't told you what vector. Here's the tricky bit. So this is the formula for the magnitude. To figure out the direction of the cross product, sorry, I need a prop to do this. Step one. Okay, have your attention. This is really important. Step one for finding the direction of a cross product. Take out your left hand. Oh, unfortunately, what's my left is going to be your right. All right. Anyways, we'll do it this way. Take out your left hand. Everybody should be doing this. Abby, are you doing this? Dylan? All right, here we go. Take out your left hand and sit on it. Okay. First thing you do, sit on your left hand. If you get the wrong hand, you're screwed. So sit on your left hand and then hold up the one that's left. Okay, your right hand. Bad choice of words. Okay, you use your right hand. So the way you calculate a cross product, the direction of a cross product, is called the right hand rule. And you use the right hand rule whenever you have a right-handed coordinate system, like we do. So you want to use your right hand. And the way you're going to do this is you're going to take your hand, and so you have two vectors, A and B. You're going to take your right hand, and if I want to do A cross B, the order really matters, so you got to be careful. A cross B. You take your hand, you align your hand in the direction of A, and then you curl your fingers in the direction of B using the angle less than or equal to 180. So between two vectors, you can either say there's an angle less than 180 or greater than 180, or I guess equal to 180. But you want to use the smaller of the two. Okay, so you curl your hand through the smaller angle. It's clear when you go to do it. All right, so I'm looking around this room I'm in. I don't have many props. So I tell you what I'm going to do. I'm going to go get some props, and I'll be right back. Ta-da! Wow. It's like I had magic powers. I have props. Very good. Okay. How are we going to make this work? A cross B. So let's call the white ruler A. The normal ruler we'll call B. A cross B. Now everyone needs to do this with me. Okay, so I'm going to hold these up, and you need to do the same thing. So I'm going to form them like a parallelogram. Remember I drew them, or if you notice, I drew them tail to tail. So I'm going to hold them in my hand like that. So I have A cross B. So with my hand, I am going to align my hand along A. And notice this is the small angle as opposed to the larger angle around the backside. So I'm going to take my hand along A, and I'm going to curl my fingers towards B, and the answer goes along your thumb as you hold it there. So the answer will point in the direction of our Teflon stick here. Okay. A cross B. So you curl it from A to B, and it points in the direction of your thumb. Let's try a couple, because it's not hard, but if you read about it or if somebody just says it, it's like, what the heck? All right, let's try another one. Hold them up here. Whoa. Okay, here we go. I've got I've got A cross B. So I take my right hand. Don't use your left hand. If you use your left hand, it comes out with exactly wrong. It comes out with a minus sign. A cross B. A cross B. So it ends up going into your eye. A cross B, and the answer is into your eye. Just for fun, well, I've got them right here. Let's figure out B cross A. So everyone needs to do this. You need to do this with me. It's because this comes up in torque, it comes up in Calc 3, it comes up in dynamics. I assume they do something, maybe not in linear algebra, maybe, I don't know. And it definitely comes up in physics 2. So it comes up in your future courses. So if you get the idea now, it's like free points all the way through. So, and strength of materials would have it as well. Differential equations has it too. So this idea is going to happen. This cross product thing is going to happen over and over. All right. So A cross B was into your eye. Okay. So you kind of, as I hold it. All right. So you, all right. B cross A. Let's work that out. B. I can't do that. B. I've got to go to the back side. B cross A points into the board, points perpendicular. So what does that mean? Sorry. It means that A cross B equals minus B cross A. So when you have cross products, it's not commutative, it's anti-commutative. You get a minus sign when you swap the vectors. So that means you have to be really careful when you multiply them. And you have, a lot of times when we multiply numbers, we reorder them for free. We swap them around, blah, 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 whatever. When you're doing cross products, it's not so simple because multiplying them one way gives the opposite of multiplying them the other way. So take care. Do things carefully. All right. So let's practice and figure out how to do this in components. Or actually, what we're going to do, we're going to work this out in components. We're going to go through this process like we did with dot products. I'm going to say it a little bit more formally. Actually, I don't even know if I'm going to do that. I'm just going to go through it in components, and we will work out how the unit vectors multiply. And then once you know how the unit vectors multiply, it has the same bilinearity. It's an antisymmetric, but bilinear. It's linear in both factors. So if you can work out how things behave, how the unit vectors, the basis vectors behave, then you can work any other vector out. So we have this formula for the magnitude, and then we have this right-hand rule. It's the right hand, not the left. And then I'm going to have you go through and, or on the board here, we're going to work out the formula for the components. And that gives you a more algebraic way to do things. And then for this class, that's enough. In another video, I'm going to give a third way. In addition to the magnitude formula here, the right-hand rule, and then the formula that's coming, I'm going to give a third way using determinants, which are things that you will see in linear algebra. And the third way is faster if you have arbitrary vectors, but in physics 1, we won't have just random vectors, poking out in 3D. So you won't need the determinant method. And in fact, it doesn't give a different answer. It's completely consistent with what I just showed you and what I'm going to show you in a minute. It's just faster and with some practice. But not, most of you haven't had linear algebra. So that's how that goes. All right. Okay, I'm going to write this out over here. A cross B has a magnitude of A, B, sine of theta. Oh, I wanted to say, remember what I said about the dot product knowing about parallel information and the cross product knowing about perpendicular information. You can already see that from here. Because when you have a dot product, the cosine of the angle is 0 when things are perpendicular. Well, for cross products, you get sine of theta when the angle between two vectors is 0 or 180. When they're parallel, the cross product gives 0. Okay, so the cross product is not 0 when they are perpendicular. It is 0 when they're parallel. You can see that also from thinking about the parallelogram. If you have parallel vectors, the parallelogram that they make is going to have 0 area, because it's obvious. There's another, maybe deeper way to think of it. Since I have props, I will use it. Okay. In 3 dimensions, if you want to have some process which takes 2 vectors and spits out a vector, you're kind of constrained as to how you can do that in a way that makes sense. Because it has to be something which makes sense for any 2 vectors, and well, if I have A and I have B, and I don't really want to bias it towards A or B, then the answers can't really point towards A or B, and there's not really a natural way to define something parallel to them. I guess you could maybe try to define something along the center line or something. I don't know. But in fact, well, if you did that, that's just what we get when you add vectors. A plus B kind of would go along the diagonal line. So we've already used that one. So we can't put a vector along the center line, and we don't want something which prefers one or over the other. So that means it can't be, the answer of A cross B cannot be in the same plane as A and B, because there's just not a unique way to define such a thing. So basically, you're stuck with, in 3D, the 3rd dimension. So A cross B has to be something in the 3rd direction. And okay, you end up with the formula we have there. And when 2 vectors are collinear, when they're parallel, suppose that, when they're parallel, when the angle between them is 0, the only possible vector you could get is 0. Think about that. If the only way to define a cross product between 2 vectors is to choose something in the perpendicular direction, and then you try to multiply 2 parallel vectors, well, how can you uniquely choose something perpendicular to these vectors if they're parallel? Because if they're parallel, you don't get one direction, you have a whole plane of directions perpendicular to these. And so if you have a whole plane worth of directions, which are all equally perpendicular to this, and yet, again, how are you going to pick one and say it's special? You can't. And so the only way out then that's consistent is to say that the cross product between parallel vectors needs to be 0. And that's kind of the only special vector that you can think of. So that's a different way to say it, and you kind of get the same. You get it's just a different perspective on things. I don't know if that probably is a little different than how they would say it in Calc 3, but it all hangs together. All right, now having tried to give you that perspective, let's talk about the cross product between unit vectors. So if I want to work out x hat, oh, you know what? Before I do this, I need to put in a coordinate system. x, y, z. Okay, so if I want to do the cross product between x hat cross y hat, x hat cross y hat. So let's kind of picture that. I have x hat cross y hat. They're perpendicular, so their dot product is 0. Good. Their cross product is not 0. In fact, it's going to be, you have length 1, right? Because the formula for cross product is magnitude of A times the magnitude of B times the sine of the angle between them. The magnitude of x hat is 1. The magnitude of y hat is 1. The angle between them is 90 degrees. Sine of 90 is 1. So x hat cross y hat is has magnitude 1. Great. The answer is going to be perpendicular to both x hat and y hat. Well, think about it. The vector perpendicular to x hat and y hat is either, and with length 1, is either z hat or minus z hat. So let's figure it out. Okay, so I'm going to try to line these up. Here we are. Okay. Okay. So, I think I had these swapped from before. Let's try that. All right. Here you go. You're looking at the quadrant, and here I have, I'm trying to get a parallel here. That's really unfortunate. All right. X, Y, and Z, positive Z is going this way. Negative Z would be down. Okay. So X hat cross Y hat. Do it with me. Bend your fingers towards from X hat towards Y hat, and your thumb points up. So X hat cross Y hat equals Z hat. Take a second and convince yourself that y hat cross x hat equals negative z hat. It's the same thing, just reverse the order. Go through to your hand, you gotta turn it around and whatever. You get the idea. Just do it. Take a second and do it. I'll wait here. Y hat cross z hat. Or sorry, y hat cross x hat. I'm sorry. I've been at this for, I don't know, 9 hours, so getting a little loopy. Y hat cross x hat gives you minus z hat. All right. Similarly, so I'm going to erase that because if you swap two, you always get a minus sign. So the important ones are the ones that are positive. You can get all the others from that. You get that y hat cross z hat equals x hat, and z hat cross x hat equals y hat. Sorry, lost my train of thought. Okay, these are the positive ones between the basis vectors. If you do something like x hat cross itself, well, x hat is parallel to itself. The cross product between any two parallel vectors is 0. So the cross product doesn't know about the diagonal stuff. It knows about the off diagonal stuff, but it also it combines them in a special way so that x, y gives z, but y, x gives minus z. Okay, so take a second and show or confirm to yourself that those are all correct. All right, now I'm going to go and write those over here in our toolbox of things that we know. X hat cross y hat equals 0. Y hat cross z hat equals 0, and z hat cross x hat equals 0. Oh my gosh. strike that. X, Y gives Z. Y, Z gives X. ZX gives Y. I apologize. I'm just, if you can't remember, if you can just remember the first one, X, Y gives Z, then I kind of imagine these are all on a wheel, like a big steering wheel. So X, Y gives Z. So if you're going around in a counterclockwise fashion, you get a plus sign. If you go clockwise, you get a minus sign. So that sometimes helps me remember what's going on. Okay. There we go. Okay, let's work out then for arbitrary vectors. So actually, let's just pick a specific vector with components and stuff, and then we will do the cross product, and we'll see how it goes, and I'll just give you the final formula, and that'll be really what you need, I think, for the homework on dot products and cross products. So let's imagine I had 2x hat plus 3y hat, and I'm going to take the cross product with, let's just do x hat plus y hat, something simple. Okay. And I'm going to write, I'm doing this because I'm kind of working this out the long way. I chose something which is pretty simple. The formula I give in the end will be able to handle all 3D cases. Okay. All right. So the cross product distributes. That's the kind of stuff I forgot. I omitted when I didn't do that kind of formal stuff. You can distribute across the cross product, but you cannot commute things. You have to be really careful with the ordering. Okay. So this is going to give me 2x cross x hat and 2x hat cross y hat. Well, x hat cross x hat is going to give me 0. So the diagonal stuff goes away. I don't worry about it. Focus on the things that aren't 0. X hat and y hat. They will pair up to give me something that survives. 2 times 1 gives me 2x hat cross y hat. I'm just going to write them down and be careful with the ordering, and then we'll rearrange it afterwards. Plus, so I didn't handle that one, 3y hat, so I get 3 times 1, y hat cross x hat. And then finally I have 3 times 1, but then I get y hat times y hat. Y hat cross y hat is 0. So I'm not even going to bother to write down the stuff that's 0. If I know it's 0, it's 0. Done. Okay? Good. X hat cross y hat gives me z hat. Y hat cross x hat gives me negative z hat. So this becomes 2z hat minus 3z hat equals negative 1 times z hat, or minus z hat. Okay? See how I unwound those? You can always distribute, that's fine, but notice how when I distributed, I was very careful to preserve the order that I multiplied these things. That's what happens. When you don't have commutativity, then you have to be careful. So keep the order, and then use the properties to flip things around to get your answers. Okay, I'm going to write down the formula for arbitrary vectors. Okay, if I have a vector A with components, as usual, AX times X hat plus AY times Y hat plus AZ times Z hat. I have a vector B, which equals bx times x hat plus by times y hat plus bz times z hat. Now, in class, if we were in class right now, I'd be saying, pull out your whiteboards, do it. Multiply it out. It'll be as awful as you think it's going to be. You can drop the diagonal stuff, but keep track of everything that's there. Since I can't make sure you're doing it, please do it. If you can get the answer for this, you're golden. You can do anything, okay? So what's going to happen is I'm going to work out, maybe I can sort of do it here. A cross B. Let's think about that. Whew, I've got to write them all down. Multiply them, and you distribute, and you get out every little bit here. You're going to end up with the x component times the y component, x component of A, y component of B. That's going to give you something with a positive z component, z hat. The other time you can get something in the z direction is if you do the y component of A times the x component of B. But when you do that, when you compute A cross B, you end up with y hat cross x hat. That's minus z hat. So, for example, inside this big mess, there's a bit of it, which is going to be ax times by times z hat. But before I do that, I'm going to regroup things. Minus ay bx times x hat. Oh, sorry, z hat. Oh dear. Okay. Fine. Now let's look at our next term. We have ax. That will all, it distributed to hit by, but it's also going to hit bz. I'm going to get ax bz, but that's going to give me x hat and a z hat. X hat times z hat, x hat times z hat, that's actually minus y hat. So I get a minus on between. So, oh, Jesus. So this is going to be minus ax bz, and then I do it the other way. I'm going to get az bx. That's going to be in the good order. That's going to give me a plus y hat. But since I have a minus sign out front, I'm going to write that as a double negative. And then let's work out the last little bit here. So to handle the thing that's going to be proportional to z, the thing that's going to be proportional to x, the thing that's going to be proportional to y, the part that's going to be proportional to x is what you get when you multiply ay and ay and bz, and then az and by. So ay times bz gives me y times z. That's going to be y times z. That's positive x. So I get ax times bz. Sorry, getting tired. Ay times bz with a positive x. So I get plus ay times bz with a positive x hat, and it'll be minus az by times x hat. Okay, that is the general formula for a cross product between any two vectors in 3 dimensions. And in general, that's what it would be. For physics 1, we won't use this. I think there's one problem set on cross products where I think you use it there, but we don't use this. Our vectors tend to be very simple. They live in a plane, usually the XY plane, and then they point in the Z direction. In linear algebra, statics, dynamics, physics 2, strength of materials, calculus 3, differential equations, you use these concepts. And they may all emphasize different aspects of it, but this is the real deal. This is the full formula. If you can go from up here to down here by multiplying it all out, being really careful, watching the minus signs, rearranging things, you can do anything. The important thing to remember about cross products is that they know about perpendicular information and they don't know about parallel information. The cross product between parallel vectors is 0. And so, so that affects what happens there. Because we haven't had too many problems in 3D, I want just a bit of notation. It's kind of, well, the first time I saw it as a student, I didn't know what I was looking at. Just a comment, because all of our problems basically live in the plane, so we'll have X and Y. So here's X, here's Y. Okay, if that's X and that's Y, think for a second, where is Z? Well, how about this? Maybe you don't know, maybe you can't picture, but we know that X hat cross Y hat points in the Z hat direction. So let's do X hat, curl my fingers towards Y hat, Z hat's gonna be into your eye. Z is out of the board. If this is X, this is Y, Z is out of the board. Now, we've been writing X hat, Y hat. How do we write down the third direction? Positive Z hat is going to be, here's how people write it, I kid you not. Z hat is written like that. And similarly, this equals minus Z hat. What am I looking at? That's what I said to myself. What you're looking at is an arrow shooting you in the eye. Okay, so Z hat comes out of the board, which means Z hat goes into your eye. Ouch. On the other hand, if it's an arrow going into the board, negative Z hat, you see the feathers, or now that I live in Western New York, I've been told they are called fletchings. To me, they're just feathers. Okay, so the last thing you see when you, if in the Z hat direction, the last thing you see is the tip of the arrow, so you get a dot. If it's in the negative Z direction, the last thing you see are the feathers minus Z hat, so you get an X. Okay, that's stuff here for today. Next time we will talk about work and use dot product concepts. Well, we're going to talk about work and energy, and that will involve dot product concepts. Cross products will come up when we talk about torque and also angular momentum.